Alright, hi everyone. Welcome to this video where we'll be going through topic 11, topical 10 series on the reactivity series. Now, in this video itself, we'll be covering certain of the questions that are more challenging, but for the rest of the answers to the questions, feel free to refer to the document that's been sent out to the class. Let's kick off first with question 1, right? So, for question 1, it states that the copper 2 oxide is actually reduced to copper in an experiment that's shown over here. So we see that there's actually copper 2 oxide that's being heated up, and then we notice that hydrogen gas is the chemical that's being used for this reaction. So what's happening in this reaction is hydrogen gas was actually reacting with copper 2 oxide, and this process, it forms our copper solid because of the reduction, and water or steam will be produced, right? So this is basically a concept that we learn as reduction by hydrogen. So metal oxides can go through this depending on the type of metals that we're looking at. So in this question, they're actually asking the students, why is the hydrogen kept flowing even after the Bunsen burner is turned off until the whole tube is actually cooled down? So this question here actually doesn't talk about any of the things that we have learned in the syllabus or the notes itself, but it actually wants the students to think a bit deeper in terms of what could have happened if hydrogen were to be switched off. So let's go through the scenario. Assuming that hydrogen is off, what will happen is that we notice that there is an opening over here and there's an opening over here, right? So naturally, once hydrogen gas is off, there will no longer be any more gas entering. There will no longer be any more gas of hydrogen leaving out from the top. So what will happen then is that any form of air from the surrounding can then try to enter through the opening of this test tube, right? So what happens is that if hydrogen is off, surrounding air will actually enter the setup. Now, when surrounding air comes in, usually the concern is that O2 will then react with any form of which in this case is the metal, which is the copper metal that is remaining behind. Because remember, the test tube is still very, very hot, right? This is the reason why if we actually don't switch off the hydrogen gas, right? If you don't switch off the hydrogen gas, that's how we ensure that we prevent any form of air from entering. But once you switch it off, any air that comes in will bring along the oxygen, and the process will cause a reaction between the copper as well as the oxygen, and you end up with your copper 2 oxide again. So in this case, the setup, the purpose is actually to prevent the copper from reacting with the air. Okay, so that's for question 1. Let's move on to the next page on question 7. Question 7 states that lithium reacts with water to form solution P and gas Q. So this is a recap on the reaction between metals as well as water. So I hope you still remember that in this reaction between metal as well as water, you actually form a metal hydroxide, and the gas will be hydrogen gas. And of course, in this case, this metal hydroxide will therefore be lithium hydroxide. Lithium being a chemical that is found in group 1, when it forms an ion, we know that it will actually be Li+. Hydroxide, we do know that it's a polyatomic ion, which means it must be OH-. So this will then give us a formula of LiOH, right? Which means that C and D are immediately out. Of course, by then you'll know that it's hydrogen gas, B should also be out, right? So I think this will help to give you a sense of what's going on. But let's move on to talk about the second part of this question. When solution P reacts with dilute sulfuric acid. So solution P is this lithium hydroxide. So moving on, lithium hydroxide reacting with sulfuric acid. Now this is what we know as neutralization, right? So in neutralization, the product will be that of a salt and water. So in this case, the salt will be lithium sulfate and water. So in terms of the ions that we're looking at, like what I said just now, lithium will be Li+. Sulfate is also a polyatomic ion that we need to know is SO4 2-. Now, in case you have already forgotten about how your formula comes about, remember, if you have a Li+, a single plus, and SO4 2 minus, you need to balance up the charges. That's why you need one more of the Li plus, and collectively this will be LiSO4, Li2SO4. Right, and that's for question 7. Moving on, let's take a look at question 8. Now, when it comes to question like question 8, as a student, you do need to process the data in a calm and composed manner, right? So we need to do this in a very structured way. Okay, so what do I mean by that? In this chapter, there's two things that you must remember. Number one, the more reactive a matter, the more vigorous its reaction will be. So to take note, so what I'm trying to say over here is that if the matter is very reactive, the matter itself, the reaction will be very vigorous. At the same time, there's also another concept that you must remember. The more reactive a matter is, the more stable its compound will be. Now, what does this mean? This means that the compound will not want to react. Now, take a time to really look at these two statements, copy this down, try to remember what it means, because when you look at these two statements, what they're trying to tell you is that if you just look at the matter by itself and it's very, very reactive, it just means that the reaction will be very, very intense. And that is what all students will remember, statement 1. But what a lot of students forgot is, when you look at a reactivity of a matter, and then you look at its compound, okay, it's different. The more reactive a matter is, the compound actually becomes stable. When the compound becomes stable, it means that the compound actually does not want to react. Now, this will mean that when you look at reactivity of a metal, and you are asked to think about the compounds like carbonates, nitrates, etc., you must remember that there is this statement number 2 that helps us to understand what's going on. So let's apply this to this particular question. In this question, they are talking about reactions of 3 metals, W, X, and Y, or the compounds of these metals. First statement says that the oxide of W is reduced by both heating with carbon and by heating with hydrogen. So what they're trying to say over here is that the oxide of W can react. Okay? Second statement, the oxide of X is not reduced by heating with carbon or by heating with hydrogen. So basically, oxide of X cannot react in this context. Last one, W displaces Y from an aqueous solution of the sulfate of Y. So what does the last sentence tell you? Because it's about displacement, right? And it's between metals, right? So this will allow us to understand that this means that W is more reactive than Y. So armed with this set of information, let's see how do we go about arranging the chemicals. So we know that W is more reactive than Y, right? So definitely W must be under the more reactive side, whereas Y must be at the less reactive side. But the question is that how do we know about between W and X? Now, students who don't understand about statement 2 over here, what they will go away thinking is that, oh, because X cannot react, oh, that means W is more reactive than X. But this is actually very, very wrong. Because if you look at the statement, they are talking about the oxide of W. They are not talking about W as a chemical being able to react. They are talking about the oxide of X. They are not talking about X as a chemical, whether it can react or not. So, in other words, what we're trying to say over here is that when you know statement 2, and you read these two deduction, as a student, what you realize is that when oxide of X cannot react, it means that it is actually very stable. And if it's very stable, it means that X is actually considered a very reactive metal. Likewise, if oxide of W can react, it means that it is not stable. If it's not stable, it will mean that W is actually a not reactive metal. So from this, as a student, what you're supposed to be able to infer is that, based on statement 1 and 2, right, we should be able to tell that X is more reactive than W. So let this sink in for a while, right? Let this sink in for a while, right? And if you're not too sure what we are talking about over here, pause the video or play back the video and take a look at it again to see if you understand the concept that is being described over here. Okay, so now let's take a look at how do we arrange everything. X is more reactive than W. W is more reactive than Y. In other words, X will be the most reactive chemical, followed by W, followed by Y. This is based on the conclusion using W is more reactive than Y and X is more reactive than W. So we're going to try out a few more questions in this video that uses the same concept, and we're going to flash this statement 1 and 2 again, and we're going to apply it as we go along. Alright, so whenever you come across a question that talks about the reactivity in MCQ, or even in structured question, remember about these two statements. Let's take a look at question 10. So you see that question 10 is again comparing about reactivity, right? So let's bring back these two statements over here again. Then we see which one we need to apply accordingly. Okay, so this one says that pieces of lead, magnesium, iron, and an unknown metal X were placed separately in test tubes containing aqueous solutions of their ions. Right, so the following observations were made. When you put the metals with the ions, and you see whether there's a reaction, so cross is no reaction, tick is as a reaction. So in this setup over here, what we can see is that the question is actually trying to test on statement 1. Because they want us to see the more reactive a metal is, the more likely it is able to do the displacement on the other chemical. Right? So the one that has more tick, like magnesium in this case, will therefore be a lot more reactive. So if I look at magnesium, if there's a tick between magnesium and lead, I can conclude that magnesium is more reactive than lead. Where if there's a tick between magnesium and iron 2, it means that magnesium is more reactive than iron. Not iron 2, just iron as a metal. If it's a tick between magnesium and X2+, it means that magnesium is more reactive than X as a metal. Therefore, the displacement can happen. Okay, so this will then allow us to see that actually magnesium should be the most reactive chemical. Likewise, it should also allow us to see that lead should be the least reactive chemical. Then we take a look at iron. When we look at iron, we realize that iron can actually react with lead too. So iron is more reactive than lead. Iron can also react with X2+. That means iron is actually more reactive than X. So this then allows us to conclude that the answer must be that is magnesium followed by iron, followed by X, followed by lead. Okay, so using the same concept, we're going to take a look at other questions again that talks about comparison. So remember about my two statements over here. For this question, we are using statement 1 to help us. Let's take a look at statement question 14, right? Then we can take a look at question 15 as well. Same thing, I'm just going to bring back these two statements here. Okay, then you try to use this to help you with the answering, right? So the thermal stability of metal nitrates is related to the position of the metal in the reactivity series in the same way as carbonate. Now read the question carefully. This is now a metal compound. So should statement 1 or statement 2 be the concept that we think about? Okay, and it should be statement 2, because the more reactive a metal is, the more stable its compound will be, right? So in other words, when you look at this thing now, even though all of you would have been very diligent to remember about your reactivity series, right? This will tell us about the reactivity of the metals, but this question is about a compound. So if you want to know that you will decompose, if you know that you will decompose, it will mean that the metal compound must be unstable. That's why it can decompose, right? So if you want it to be unstable, it will then infer, if you use statement 2 to help you, it means that the metal should be a less reactive metal. If not, it's not gonna react. So if now then you look at the 4 options over here, you know there's iron, there's potassium, there's sodium, and you realize that the one that's the least reactive metal over here is actually the one with silver. So then therefore the compound of silver will likely be able to decompose when it's being heated up. So this question requires you to apply statement 2. Now, if you are a student that don't bother about statement 2, what you end up doing is that you will see that this is potassium, and you think that, oh, potassium being a reactive metal, okay, everything is about potassium being reactive. But it is the opposite of what's going on. So do take note of this part, alright? Now let's go to question 15. Question 15. P is more reactive than metal Q, which is more reactive than metal R. So the question starts off by telling us that P is more reactive than Q, which is then more reactive than R. Sulfates of P and R are colorless. Sulfate of Q is blue. So there's a few more information about the sulfate. So P sulfate, R sulfate, and then we have Q sulfate. Right? So this is blue, this is colorless, and the first one is also colorless. Okay. So this question seems to want us to link this reactivity with one another. Therefore, it's likely to be talking about displacement, so that we see whether there's a reaction or not. So let's take a look at it. Displacement as a concept, just a reminder for all students, metal displacement is not just about if you see two different metal, there must be a metal displacement. Okay, metal displacement is that you must use a metal plus another metal compound. So I'm going to use just metal Y and metal X as an example, right? If you want a reaction to happen, the metal that's solo, which in this case is metal X, the one that's not in the compound, if it's more reactive as a metal compared to metal Y, then a displacement will take place. So do take note, only if the single metal, the solo metal, in comparison to the metal in the compound, there's a difference in reactivity, that means the one that's outside by itself is more reactive, then the reaction will happen. Okay, so must you know that this is how displacement works. So now, P in a solution of Q. So P and Q, we know that P is stronger than Q. Should there be a displacement? Yes, there will be a displacement. Whether the color is correct or not, we'll take a look at it later on. Q with P, no. Q is less reactive than P, can't do that. Q with R, yes, there can be a reaction. R with Q, no, there cannot be a reaction. Now we'll take a look at the color. Solution of Q, based on the question, is blue. Solution of R, based on the question, is colorless. So if there is a reaction, there will be a change in terms of the color of the solution based on what we gathered in this question. Then now if you look at the whole context, it's not possible for this to be blue, right? Because R is actually colorless to start off with. And therefore, that's why the answer will actually be option A. Okay, so I hope you can see how the two statements that I've been talking about over the past few questions is applicable whenever there's a question talking about comparison between different chemicals, and you know that it's about reactivity series. Okay, then now let's move on to question 18, which will be the last for the MCQ, I believe. Question 18, talking about carbonates of metal X and Y. So let me bring back my two statements again. And since it's about a compound, I'm trying to compress it further. Since it's about compounds, right? Therefore, you should be looking at statement 2, because these are all the compounds of metals. They're not looking at the normal metals. Okay, so both of these are being heated up. The carbonate of metal X changed color, that means reacted. Okay, carbonate of metal Y did not decompose, that means did not react. So as a student, remember statement 2 says that the more reactive a metal is, the more stable the compound will be. This will in turn mean that Y as a metal is very reactive. That's why its compound is very stable. This since for X is reacted, it means that X is not a reactive metal, as you can see that its compound, X carbonate, is actually not very stable. Okay, so keep that in mind. Right. So which statement is more correct? Which statements are correct? Sorry. Metal X is more reactive than metal Y. This is definitely wrong, because we already proved that metal Y is actually more reactive. Right. Both metal carbonates will react with dilute nitric acid to form carbon dioxide. This is actually a correct statement. Why? If you go back to your notes on acids and bases, we know that all acids react with carbonate to form salt, water, and carbon dioxide. So this is correct. Metal X could be a transition element, right? How do we know whether metal X could be a transition element or not? And the hint actually comes from this color bit, right? So we know that transition elements or transition metals actually, right, that has a tendency to exhibit different color in different compounds. Okay, so this allows us to then know that chances are, since there's a change in color, this metal X could likely really be a transition element. So statement 2 and 3 will be the one that we go after, and therefore the answer is actually D. So this question here, actually just for everyone's information, we're actually looking at this compound called copper 2 carbonate. So very likely is that X is copper, so carbonate of X will therefore be copper 2 carbonate. Now why do I say so? Because copper 2 carbonate is actually one of the chemicals that we commonly see in our lab or in our practical session. It is actually a green solid. But when you heat up copper 2 sulfate, you will end up with this thing called copper 2 oxide plus carbon dioxide gas, and copper 2 oxide is actually a black solid, right? Then carbon dioxide you can test with lime water, etc. Right, so this is actually what this X carbonate is lah, just for information. But of course you don't need this information to do this question. Okay, so that's for question 18. So use this to apply to any other questions that you see along for the MCQ, and later we'll talk about the structured questions as well. Alright, now let's take a look at the structured questions. So for the structured questions part, I'll be going through those questions that have been highlighted in blue, right? As we go along, please take note of the things besides just looking out for the answers, right? So do annotate as we go along. Okay, so for question 1 over here, we realize that the question is actually testing a lot about the reactions between acid as well as the compounds of certain metals. So for the first question itself, they mentioned about explaining why lead can react with nitric acid, but gold does not. So first up, let's try to recall about our reactivity series. So we know that our reactivity series is as such, right, starting from the most reactive metal to the least reactive metal. And of course, all of us know that lead, in comparison to gold, there's a difference in terms of their reactivity. But the difficulty in this question is actually the marks that's being allocated. So this question actually has 2 marks being given, and I think most students who have identified that lead is more reactive than gold, for the answers will actually only score 1 mark, right? So what exactly is the second mark that we're looking out for over here? So for this first question, what we actually want the students to be able to identify is that, number 1, definitely there's a difference in terms of the reactivity, but also going further to explain about what it means in terms of this reactivity difference. So in the metals chapter, or rather in the reactivity series chapter, we have learned that when something reacts, or rather when a metal reacts, the idea is that the metal will actually lose electrons to form a positively charged ions. So this is where, because of the marks that's being allocated for this question, you do have to elaborate to share about this tendency to lose electron and ability to form positively charged ions. In a typical question whereby there's only 1 mark being given, just stating the first point will be good enough. But over here for this question, they actually want a bit more, hence the term used explain. Okay, so do take note for question 1A. On question 1B, we move on then to look at the different acids, right? About how they cannot be used to remove the compounds of lead, but dilute nitric acid can actually be used. So when you look at this question, what you need to ask yourself is, number 1, all these are acids, and when acids react with the lead compounds, what could be the difference between these 3 different acids that's being used over here? Now, so it's not a case whereby they are strong or weak acids, because all these 3 are strong acids, so it shouldn't be about whether they are strong enough to react with the lead compounds. Next, we take a look at what kind of products can they form. So based on this question here, you realize that you can either form your chlorides, you can either form your sulfate, or you can form your nitrate. So this is the key difference between using 3 different acids. So now there must be something about these 3 different types of products and how it makes it different when you use dilute nitric acid as compared to hydrochloric acid and sulfuric acid. And this actually taps on the earlier chapter in Sec 3 on salts and solubility. So we all know that whenever you use an acid with a chemical, right, there's a tendency for it to react and to form salt. In the case of using hydrochloric acid and sulfuric acid, what will happen is that you actually form this insoluble layer of lead 2 chloride or lead 2 sulfate, and this will then prevent further reaction from happening. So this is the reason why these 2 acids are actually not used to remove the compounds of lead. However, when you use a nitric acid, this will actually form lead 2 nitrate, which is a soluble chemical, Therefore, it will not hinder any further reaction. This then allows for all the compounds of lead to be reacted and then to be removed. So this question, being a bit more complicated, actually tests on student on whether they are able to differentiate between the solubility of the product that's being formed. Okay, so when you read a question, do analyze and do try to compare and identify what exactly is the concept behind it. See part 1. Different metal ores may contain impurities, right? And then the question went on to ask why is aqueous ammonia only able to identify one of the ions in the solution. So in this question, they had mentioned about 3 different types of ions: lead, zinc, and aluminum. So as a student, what you need to do over here is to recall about how aqueous ammonia can be used as a test for K ions. Okay, so I hope you recall that in the chapter on QA, you have learned that lead, 2, zinc, as well as aluminum ions can actually react with aqueous ammonia. And the process, they could form white precipitate. However, some of them, or rather, there is a difference between what will happen to the white precipitate if an excess of aqueous ammonia is being used. So first, aqueous ammonia can actually only be used to identify zinc ions, and that's because it will react to form a white precipitate that is soluble in excess aqueous ammonia to form a colorless solution. However, when aqueous ammonia is being added to lead or aluminum ions, you actually result in the same observation of an insoluble white precipitate. Now, this is the part in QA whereby you will actually be introduced to the idea of test for cations, and you'll recall that for this particular test, there are quite a few ions that can result in a white precipitate. So let's just run through what are those few examples that can form a white precipitate for cation test. So the ions that can do that, they are zinc, aluminum, lead, as well as calcium. Now, but in order to differentiate them, we actually can recall what actually happens to this white precipitate if aqueous sodium hydroxide or aqueous ammonia is being used. So in the case of zinc ion, what happens is that the white precipitate will be soluble in excess of the chemical to form a color solution. In the case of aluminum, it will be soluble for the case of sodium hydroxide, but insoluble for the case of aqueous ammonia. Likewise for the case of lead, and then for the case of calcium, it will be insoluble for the case of sodium hydroxide, but you will not form any PBT if you were to use aqueous ammonia. So this is the part that requires a bit of revision. So if you are still not too sure about what exactly are the results for the cation test, do take some time to revise this bit because it's also useful for your practical exam. So the next question, which is a follow-up question, then asks how can we differentiate the other 2 ions. So these 2 ions that we are looking at is that of aluminum as well as that of lead. So to differentiate these 2 ions, we actually base it on the concept of solubility, and we can either, number 1, add sodium chloride solution so that the sodium chloride will react with the lead ion, and then this in turn will result in the formation of lead 2 chloride, which is an insoluble white precipitate. Alternatively, you can also add an iodide solution, which that can also react with the lead 2 ion, and this will then form a lead 2 iodide precipitate, which is a yellow precipitate. So this part 2 actually requires the student to know that you can use the idea of solubility to help you to differentiate between lead as well as aluminum ions. And then the very last question on how to test for nitrate ions. So the test for nitrate ions, pretty straightforward. You're supposed to add sodium hydroxide solution, a piece of aluminum foil, warm the mixture, and then test for any gas using a moist red litmus paper. And once there is any nitrate ions that's being present, the moist red litmus paper will actually turn blue because ammonia gas will actually be formed. So this will be the last 3 marks of this question. So you'll notice that for question 1, for this particular chapter, it actually tests a lot on the concept of qualitative analysis, right? Besides just testing about reactivity series for question 1A, right? Other than that, most of it was about solubility as well as QA. And now let's take a look at question 2. Now in question 2, the question is actually asking about the protection of steel pipe, right, from the process of corrosion, right? So they mentioned about how this is actually attached to blocks of magnesium as shown in the diagram. So this question is asking about how is magnesium protecting the iron, the steel itself from rusting, and this has to do with the concept known as sacrificial protection, right? So a quick recap on sacrificial protection and in terms of what it means. In sacrificial protection, what we do is that we use a more reactive metal, and the metal will actually corrode, that means react with the air as well as water, in place of any iron, or in this case the iron that's present within the steel. Right? This actually prevents the iron from going through rusting. So a quick explanation of this process basically will be that magnesium is a more reactive metal, and since it's a more reactive metal, it will be able to corrode in place of iron. So magnesium is more reactive than iron, and therefore will corrode in place of iron by reacting with the air and water that's present in this whole setup. How do we show this in terms of a ionic equation? Right, so if you notice over here, they are looking at this thing called an ionic half equation. Right, so the reaction is between magnesium and that of its surrounding, but we don't have to show it out because this is an ionic equation. We are focusing on just the main chemical, which is magnesium over here, and this will actually form magnesium ion and 2 electrons. So this looks a bit like the half equation that we learned in the electrochemistry chapter, right? So this shows the oxidation of magnesium. Alright, and then let's take a look at 2b, part 1 and part 2. Now 2b is now talking about oil and paint, right? Explaining about how oil and paint can prevent rusting. Of course, the difficulty in this question is actually the marks that's allocated, right? Because you are being given 2 marks, you do have to go a bit further to explain to the examiner why exactly is oil and paint so useful in preventing rusting. So first and foremost, we establish that these 2 chemicals are actually an insoluble layers, so they prevent any form of air and water from coming into contact with the iron. Last but not least, why are they not suitable? In this case, actually because these are actually chemicals. They may leak into the underground soil or water, and therefore causing contamination in the water or the soil for the plants. Hence, these are usually avoided in terms of using it in underground pipes. Hence, we use this method of sacrificial protection. Alright, and that's for question 2. Let's take a look at the next few questions. So for question 3 now, if you read the question stem over here, they are talking about the reaction between hydrogen and that of magnesium oxide and copper 2 oxide. Now, if you recall what I mentioned earlier during the MCQ part, in this context, we are looking at the compounds of the metal. So, the more reactive a metal is, the more stable its compound will be. Right? So in this case, we have magnesium and in comparison to copper. Right? So the more stable its compound will be. Right? So what we can gather from here is that magnesium, being a more reactive metal, will form a very stable compound of magnesium oxide. Copper, being a not so reactive metal, will actually form a not so stable compound called copper 2 oxide. And therefore, when the hydrogen is being passed through, the hydrogen can then react with it accordingly. So what are the changes in terms of observations? Do take note that as we are talking about observations, focus on what you can see, right? Often the time, students may write things like, oh, copper 2 oxide will react. But do take note that there is no way that we can see whether it reacts or it doesn't react. What we can see is actually a change in terms of observation. So it could be color, it could be the size, etc., or gases and whatnot. So in this case, what we can describe is that for the case of magnesium oxide, there will be no observable change. Not that there's no reaction, because we can't tell whether there's a reaction or not, but we can be very certain that there's nothing that we can observe. As for the copper 2 oxide one, we can see that the copper 2 oxide, which is a black solid, will actually turn into a reddish brown solid. Now, this reddish brown solid, in case you're not too sure, is actually our copper. So how do we explain these observations? Number 1, we need to first establish that we know that actually whether or not the reaction takes place depends on the stability of the metal oxide. So in this case, copper being a less reactive metal actually forms a less stable oxide, which can then be reduced by hydrogen to form back the metal. Magnesium, being a more reactive metal, actually forms a stable magnesium oxide compound, which should not be reduced by hydrogen gas. So the logic over here, or the concept over here, is trying to get the students to know about whether you can compare between hydrogen and the metals. Another way to explain this whole set of answers will be to compare between the reactivity of hydrogen versus copper versus magnesium. Right? So we know that magnesium is much more reactive than hydrogen, which in turn is much more reactive than copper. So then this then allows us to use the concept of the fact that magnesium is more reactive than copper and hence can reduce copper to oxide to form copper metals. So this is actually how we can apply the concept over here. So it really depends on how you want to frame your answer as well. Okay, so that's for question 3. I will not spend too much on question 4 because I think it's rather straightforward. If you have followed through the video and if you have practiced enough of the displacement kind of questions, you should be able to derive question 4. Right? Perhaps one thing to take note of is that on the next part on 4b, you're actually being asked to define what's the color of the various solutions. And that depends on whether you do look at this table and try to understand what's going on. Okay? Now let's take a look at question 5. Okay, so for question 5 is actually a question on redox reaction. So I'm going to take this chance to revise a bit on how to apply oxidation state. Right, so we look at these two setup over here. We know that in terms of the reactions between Fe2O3 to form Fe or Fe to form Fe2O3, right, we are supposed to identify which one involves oxidation and which one involves reduction. So let's start first with the oxidation state. Iron as an element, the oxidation state of Fe will be 0 because all pure elements in its original form, the oxidation state will be 0. Fe2O3 as a compound, we'll know that the oxidation state of oxygen will have to be a -2. And in this case, if you were to work out the oxidation state for iron, it will actually be a +3. Right. So then based on this thing, we can see that actually if you were to go from left to right, you actually went from Fe from +3 to 0. So this is a form of reduction. If it goes from right to left, you actually went from OS of Fe being 0 to OS of Fe being +3, and therefore this is an oxidation. So in this whole experiment, we're actually trying to focus mainly on iron. So we won't care so much about the oxygen because you can't do a comparison. Right? So how do you phrase your answers over here? Okay, let's just practice this together. So the oxidation state of, okay, so I'm trying to go through the whole standard way of phrasing the whole thing. The oxidation state of iron increases from 0 in Fe to +3 in Fe2O3, thus rusting is an oxidation reaction, oxidation process, etc. etc. Right, so what is the key term that you must be able to use over here? You must be able to describe which is the element that you're looking at, whether is it an increasing or decreasing behavior, and what was the oxidation state they're looking at. Okay, so that's number 1. Second part, the oxidation state of iron in this case decreases from +3 in Fe2O3 to 0 in Fe, and this will mean that the extraction process is a reduction process. Right, so likewise, what do we do over here? We focus on what is the oxidation state that we're looking at, whether it's an increase or decrease, what was it, and what did it become, then that will describe our changes. Right, so this is just a recap in terms of oxidation state to explain about oxidation or reduction. Let's take a look at the next question. Right, so I won't be elaborating on this bit on the steel as well as how to prevent rusting, etc. Let's take a look at question 6. Now question 6 is looking at a setup in terms of the extraction of metal from the oxides by reduction. And we can look at the trend data over here. We can see that there's different type of metal oxides, and then we have the different minimum temperature needed for reduction. The first question is asking, how does the temperature needed for reduction relates to the reactivity of the metal? So what we can do first is to look at these different metals and then see whether we can see a certain pattern in terms of their minimum temperature. So we do know that based on these metals, we can actually arrange them to see which one is the most reactive. Based on the metal, we know that calcium is the most reactive metal, followed by magnesium, followed by zinc, lead, and then copper. So in comparison, when you look at calcium, we know that the minimum temperature needed for reduction is 2100. Then you look at magnesium, it's 1600. So both is pretty high. If you go on to zinc, it's 900. You go on to lead, it's 400. And you go on to copper, it's 100. So you do see a trend. So the trend over here that we want the student to identify is that the more reactive a metal itself is, the higher the temperature needed for the reduction of its metal oxide. So do take note that over here, you are looking at the reactivity of a metal in comparison or in reference to the temperature needed for reduction of its metal oxide. Right, so do take note that you're comparing a metal and then looking at data in terms of its metal oxide. So don't use words like the more reactive a metal is, the higher the temperature needed for its reduction, because it's really about the metal oxide. Okay. Next, you are being asked to predict the minimum temperature needed for the reduction of iron oxide. So this whole setup doesn't include iron, but as a student, we do know that our reactivity series has a few elements over here. Right, so we can list out the entire thing, and we know that iron is somewhere here, and iron is definitely between that of zinc and lead. So what would this mean? Since iron is in between the two, therefore we should be thinking about the temperature being in between 900 and that of 400. Right, so any value within that will be fine, and in terms of the explanation, we will compare about the reactivity of iron, saying that we know that it's in between that of zinc and lead, then linking this back to the fact that the temperature will actually be between that of zinc oxide and lead oxide. Okay, next question for part B. Question is asking about which metal and which metal oxides are most likely to react together to give the most vigorous reaction. So the most vigorous reaction would in turn mean that it's the most, okay, we know that metal and metal oxide, if you put them together, if there's a reaction, is considered a displacement reaction, right? So a most vigorous reaction must be due to, okay, instead of most, it should be the largest difference in reactivity, right? So we should choose a metal or metal oxide in terms of the chemical. They must be very, very different in terms of their reactivity. So in this case, I'm choosing a metal that is super reactive, like magnesium, and a metal oxide that's made up of a chemical of silver, which I know that is not very reactive, because this would mean that the compound is very unstable, right? If you recall what I've been talking about it through this entire video. Okay, so the compound is very unstable. So when you put it with magnesium, you want to react very well. Right, and last but not least, the last part is pretty straightforward. The product is zinc oxide and hydrogen gas. Let's take a look at the next few questions. So for question 7 now, right, it's a database question, right? It will take a while to try to analyze and understand what's going on. Basically, this question, we are talking about aluminum and looking at how aluminum can be produced. And method 1 is through recycling using used cans, and method 2 is using extraction by bauxite, which is a type of a compound containing aluminum, and it's by the process of electrolysis. So let's take a while to study this table and see if we can gather some information to attempt the database question. Remember that for every database question, the tip for all students is that let's read it and try to compare it as we go along. So let's take a look at the recycling bit. Recycling goes through physical sorting. What happens is that you separate them using a magnet, then you actually shred, right? Shred will mean to basically use a metal to cut it up into small pieces. You heat it up to a very high temperature of 700 degrees Celsius, cool it down, then reshape it to form molten aluminum. Right? Next, on the right hand side, physical extraction and breaking up of the ore. So you take the ore, you heat it, you hammer it, make it broken up. Then you actually will be going to add in chemicals like concentrated sodium hydroxide, then allow you to separate it from the insoluble metal oxide impurities. Next, you actually have to dissolve it in an ionic solvent. So there's quite a few chemicals that we're looking at over here. And of course, next, we are going to use a method called electrolysis to form molten aluminum. Carbon dioxide is formed in the process. Then likewise, there's a cooling and shaping of molten aluminum. So based on this entire question over here, we can see that in order to extract aluminum, there seems to be a certain high temperature that's required. Okay, but do take note that for this first method on use cans, you are using aluminum, heating it up to 700 degrees Celsius, followed by cooling and shaping of molten aluminum. Molten means that it's in liquid form. Then now let's take a look at the question. Part A. Use the information in the table to estimate the melting point of aluminum. Now the melting point of aluminum, if you recall what I've mentioned just now, it must have something to do with this first column over here. Because once you heat to 700 degrees Celsius, you actually will get your molten aluminum that you can be using it to reshape the structure. So the melting point of aluminum should be somewhere slightly below 700 degrees Celsius. So I'll be giving a random number here of 690, but it should be close to 700. Or it can also be exactly at 700 degrees Celsius for this particular question, based on the data that we see over here. If aluminum melts above 700 degrees Celsius, it will mean that this step actually cannot give us our molten aluminum. Okay, I hope you can see how the data is making sense now. Next, let's move on to part B. Part B is saying that the extraction of aluminum from bauxite uses 95% more energy than the recycling of used aluminum cans. You're supposed to use the information in the table to explain why. Now, we don't expect students to know what is the extraction from bauxite in terms of the reaction, the chemistry, etc. But we expect students to know how to use the table. So, more energy. More energy could mean a few things, right? More heat. It could also mean more electricity that's being required for the reaction to happen. Be it to maintain the equipment, be it to really cause the reaction to happen, etc. So if you look at this entire table, two things should strike out to you. Number one, the temperature that's used on the bauxite extraction is higher than 700 degrees Celsius. Number two, I hope you can also see that bauxite extraction requires this process called electrolysis. And we know that electrolysis uses electricity, right? In fact, a large amount of electricity is needed for electrolysis to happen. So what is the reason for the extraction of aluminum from bauxite using 95% more energy? Number one, it involves a higher temperature. So I'm going to write short form over here of 900 degrees Celsius. Remember, we're using a data, so we have to code the data. As compared to 700 degrees Celsius in the recycling process. So this itself will mean that more heat is required. Okay, so therefore more energy will be required. Secondly, the extraction of bauxite or aluminum from bauxite, it involves a large amount or high amount of electricity for electrolysis, right? And this is actually not required for the recycling process itself. So this is a reason why the high amount of electricity will translate to more energy. Okay, so I hope that you can see that for database question, it's really about interpreting the information. You will not be able to learn all these things from the textbook or the notes, but it must be flexible to apply. Part C. The extraction of aluminum from bauxite creates waste products that could cause harm to the environment. Two of these waste products are concentrated sodium hydroxide and carbon dioxide. Why would each of these products cause harm if they were released directly into the atmosphere? Let's start with the most obvious one, which is carbon dioxide. We all know that carbon dioxide is a greenhouse gas. And with greenhouse gas, global warming, right? Pretty straightforward. Concentrated sodium hydroxide. We all know that sodium hydroxide is an alkaline. Alkaline into the surrounding, pH will be affected, right? So when pH is affected, it can affect other form of parts of the surroundings, be it animals or be it the plants, right? So this part on part C really requires you to try to think out of the box and try to link it to some of the general knowledge. So number one, carbon dioxide. Why is it harmful? If you recall the chapter on maintaining air quality, carbon dioxide is a greenhouse gas. Not exactly that greenhouse gas is bad, but a high concentration of it will cause problems. Right? And the problem will be global warming. Of course, with global warming, this will in turn result in various other issues like melting of polar ice cap, rising sea level, more disasters, etc., etc. Right? So carbon dioxide is a greenhouse gas, and hence a high concentration of it will result in global warming. Number two, concentrated sodium hydroxide. This is actually a very, very strong alkaline. And what it can do if you were to be releasing it into the surrounding is that you will change the pH. And more specifically, you will increase the pH of environment such as soil, which then can affect plant growth. right? Or if you want to talk about the water body, it can affect your marine animals, marine plants, etc. Right? So this question over here is really testing on the students whether they are able to apply it to some of the concepts they have learned. Okay, so that is for question 7. Question 7 is a pretty good question to try to practice your understanding of database, right, in the context of a reactivity series question. Let's take a look at some of the other questions. Moving on to the free response question over here on question 1 as well as question 2, right? So I'll take on these two questions because I think the concept is pretty much similar, right? So if you read question 1, they say that silicon is extracted from silicon dioxide in sand by heating the sand to 2000 degrees Celsius in a furnace with that of carbon, right? Sand also contains small amount of aluminum oxide. Aluminum oxide will remain in the silicon after reaction with carbon, and further processes are needed to remove it. What conclusion can you make from this information about the relative reactivity of carbon, silicon, and aluminum? Use ideas about reduction to explain your answer. Let's read the line in yellow again. Silicon is extracted from silicon dioxide in sand by heating the sand to 2000 degrees Celsius in a furnace with carbon. So this is a reaction that you see over here. Using our concept of reduction or using our concept of reactivity series, we can see that carbon is actually more reactive than silicon. Why? Because carbon can actually reduce silicon from its oxide, right? So therefore, there's these reactivity differences between them. Then let's take a look at the statement in green. Aluminum oxide remains in the silicon after reaction with carbon, and further processes are required to remove it. Now this would then mean that actually aluminum is actually more reactive than carbon. Why? Because the carbon cannot do anything to aluminum oxide. So this is actually how we can pull out the data. Then that will allow us to then conclude that the relative reactivity will be that aluminum is the highest one, followed by carbon, followed by silicon. How do we explain this using the ideas of reduction? Now, since carbon can reduce silicon dioxide to silicon, it shows that carbon is more reactive than silicon. This is something we have to talk about it for a lot of times in this video. And then, since carbon cannot reduce aluminum oxide, it shows that carbon is less reactive than aluminum. And that's it for 2 marks. Right, so this is a kind of a question that is pretty straightforward, just that there's a bit of context that you must read and try to understand. Question 2. Displacement reactions are used to extract elements from their compounds. We already know this. Then they talk about bacteria, so on and so forth, and they mention about solution of aqueous copper 2 sulfate and how it's being extracted by addition of scrap iron. And then you see this ionic equation over here. So what will be observed when iron is added to aqueous copper 2 sulfate? So this question is now asking about observation, right? To take note, so the question is not asking about whether there's a displacement, whether there's a reaction, but they want to test whether the student know what it looks like when the reaction happens. So as a student, I hope all of you remember that copper 2 in a solution form is usually a blue solution. So you have done enough QA. I hope you remembered about this thing. Iron 2 in a solution form is going to be a green solution. So first and foremost, the solution is going to change color, blue to green. Secondly, iron as a solid, right, is usually a gray solid, dark gray solid, etc. Whereas copper as a solid is what we call a reddish brown solid, right? So this question do test a student on their understanding about colors of common chemicals, right? In this case, iron, copper, as well as their ions. So what will we observe? A reddish brown solid will form. That is to show that the copper is being formed. Secondly, we should also be able to describe that the solution will turn color from blue to green. Now, to be more exact, there is also another way to phrase it, which is that a reddish brown solid deposit will form, right, on the gray color solid iron itself, right? This will show that the reaction is actually happening. So how would this look like? Imagine there is a blue solution of copper 2 ion, and as you do the reaction, you place in a piece of iron, Fe. When the reaction takes place, what we'll end up with then is actually the solution. So assuming that the reaction is completed, or rather it has taken place enough to see any color change, because sometimes it takes time, right? And then we actually will see a layer of the copper forming on top of the iron, right? And this is assuming that the iron has reacted, right? Eventually, it may be a case whereby all of this becoming fully red in color, for example, or reddish brown, right? So it could be this case as well. So when you're thinking of displacement, I hope all students in terms of observation, you can remember to take note of the solution as well as the solid deposit. Okay, and we have come to the end of this pretty long video talking about some of the more difficult questions of topic 11 reactivity series, right? But do take note to refer to the main set of answer key for your corrections and check in with the teachers if you have any questions. Alright, that's all.